These are the fundamentals, and Yunlu, who you just saw, is partly responsible for a number of these slides because we teach together. We teach a class at the University of Delaware, and he teaches a class that, I don't know how many, 400 people took your class last time, or more than that, a MOOC, I guess it counts as a MOOC, during the pandemic. And then at the University of Delaware, we teach a class in neutron and scattering methods generally. I'll pass the book along. I'd like to get it back. This is just to give you a sense of one of the textbooks that we use when we teach on the basics, right? So the basics of SANS. This is a Spin Echo Workshop. Why are we talking about SANS? You got to understand the structure, understand the dynamics. And that's what we're talking about. Plus, we have to introduce neutrons. The book was written by a fellow at Oxford University, professor. Makes sense. But it's sponsored by Unilever. Unilever, people who make Haagen-Dazs ice cream, right? People who make Axe body wash, blah, blah, blah. A huge company like Procter & Gamble, right, in Europe. And so, you know, it's important, right? Not just for academics, but industry. So I'll send that. You can take a look as I'm talking and pass it around. Here's where we are. You get to hear from me for the next 40 minutes. And we get a break. We always have learning goals, right? We're here to learn. And so we want to understand some basic concepts of scattering. We want to look at the idea of reciprocal in real space. We want to learn about neutrons and why should we use neutrons? You're here, you've been reading some background, but let's make sure we are all on the same page. We want to understand the basic principles of neutron scattering. And, you know, why? Well, as you just saw with these beautiful science examples, you see pictures of structure and you're looking at dynamics, right? That's the paradigm of the 21st century, right? It's 4D, right? 3D structure plus time, dynamics are important for the functioning of whether it's a monoclonal antibody, that membrane, the polymer nanocomposite. It's all about the dynamics, but the structure is important. 20th century was all about structure-property relationships. Now it's all about dynamics, and that's why you're here for Spin Echo. And we need to understand the length scales that we're probing with the technique, right? So let's get started. I'm going to talk about a little history. We'll look at Young's experiment, some basic ideas. I'm going to go through this fairly quickly because you should have a little background in it. It's more of a refresher. And we can talk more in detail. We'll have question and answer. Interrupt me if you see something that bothers you, okay? Okay, fair enough. Bragg, Nobel Prize, Bragg scattering. I think we're all familiar with it. We take a crystal lattice and we get structure in the scattering that comes out. We have Bragg's law, which relates the length scale between the atoms in this case. I'm hoping this is the pointer. No, that was not the pointer. All right. This might be. Yeah, this one's the pointer. Okay. The distance between the atoms and the interference pattern that we're about to see on the next slide. Bragg's law, right? There's some relationship between the wavelength and the distance and the angle. And a few quick examples, historical. Some of the first structures developed, right, working in X-ray scattering. This complex material wurtzite here in 1912, and you can see the complex peaks and scattering pattern that allow people to deconvolute. We're way beyond this now, right? Massive proteins and other things in crystallography. It's a workhorse technique, neutron and X-ray scattering crystallography. DNA, right? Maybe the most consequential X-ray pattern ever taken, perhaps, right? After Bragg. Rosalind Franklin, right, and Gosling, and this beautiful work here, and here's the original, right, the alpha helix. Young's double slit. I'll show you the actual experiment in a minute. There's a lot on the slide. Simple idea, right? You have a radiation source. You've got some incident wave vector. We'll talk what that is. You've got two slits. You look at a detector. You have your eye or subdetector over here, depending on what the radiation is. The path length is different for the two scattering from these two slits. So we get an interference pattern. Remember, we measure intensity as the square of the field, right? So you have a field generated here, a field generated here. And I'll go through this in some detail. I'll show you an example of this. So, and again, if you're writing a lot, I would say everything there is online. Take some notes, but remember, you've got the notes in detail. So again, what do we measure? Intensity is the square of an electric field, or a field vector, a field in general. We talk about a scattering vector Q, right, which is related to the angle and the wavelength. So that's a vector diagram. We'll talk, again, this is sort of a summary. We'll talk about these. And if you do just the vector math, you see there's an extra distance coming from the second slit to the first one. That gives us the Bragg interference. And we can write down an example. So let's take a look at this experiment in some detail. So let's look at a single slit. I think it's a little easier to visualize what I just said if we start with that. And remember, light, X-rays, and neutrons, you have particle wave duality, right? So we can look at it as a wave or look at it as a particle, but you get a diffraction pattern. And so on a back plane here, you can see, the fluctuating field, if you will, that's due to the fact that I've got a plane wave coming in here and it scatters, right? And I get this behavior. Can we learn something from this? The answer is, of course, yes. So Young's double slit, we have two slits generating an interference pattern. So we're going to get minima and maxima in the intensity when we square. Where we have constructive interference, we get a maximum. That was what we saw in the calculus a minute ago. And you can sort of visualize this and, can we learn something? Also, I'm assuming everyone in the room has some very maybe physical chemistry undergraduate rudimentary understanding of quantum mechanics, some basic level. If not, it's okay. We can talk more about it at the break if you have questions. But just remember the particle wave duality. If I put, if these are particles, right, coming through, you'd say, well, particles would come through here, particles would come through here, and I would just see two big peaks at the back plane, right? But I don't. I get this complex interference pattern because of the wave nature, right? So neutrons, electrons, photons, right? All these things. All the same in that general regard. So can we learn something? And this is an example of coherent scattering. This interference pattern is requiring two scattering, in this case, apertures, slits, and an interference. Okay, what's this got to do with small angle neutron scattering and that? Well, we're getting there, building up our understanding. So back to the double slit experiment. Again, we see this minima and maxima because of this interference pattern due to the different pathways. So it's all geometry, right, once we work out. And we have an incident wave vector and a final wave vector. So the wave coming in with wavelength lambda, we can describe as a wave vector k, and it's oriented horizontally. And then we have a vector here, and we'll talk about whether the wavelength is the same going in or out or not. That's something we need to think about. Is the energy the same, right, after going through the slit? So we observe an intensity pattern. We've lost that phase, right? The phase would be the time variation of that. And that'll come back to haunt us in some examples that you'll see during the workshop. But because we're looking at intensity, right? Okay. We don't actually look at the field itself. We're looking at the square of the field. All right. So again, Young's experiment, deep understanding of scattering can be gained by just this very simple experiment, which of course was designed to show the wave-particle duality, right, in quantum mechanics, but is useful for us to think about because now we can think of these slits as scattering centers, as atoms in our protein, right, or as atoms in the surfactants or lipids in a membrane or something, and we get scattering from those two, and they interfere with each other, giving a pattern, and we sum that up over now more complicated objects. That's where we're headed. But the principle is simple. I hope everyone sort of sees this, right? So the two slits generate things, and depending on the distance between the slits, right, that's going to affect the pattern back here. All right, what about these probes? We're here to look about neutrons, but many of you maybe have experience with X-ray or light, because that's more common in your laboratory, right? You can do X-ray, you can do light scattering in a laboratory. Neutrons, you need a big facility like this. Important aspect is that neutrons have particles nature, they have spin, and they interact with the nucleus, as we'll see. Whereas X-rays and photons are generally interacting with the electron, right? They're interacting with the electrons. So we can now get different information, right? We can use X-ray, neutron, and light to get different information. And they're also on different length scales, right? Light is a much longer wavelength than the neutrons and the X-rays, so we're looking at different length scales in the system, okay? So a light doesn't see the atoms, right, directly. It sees the polarizability of the material, which is a collective property. Okay. I like this when I was a student postdoc at Los Alamos. Roger Pinn was there, and he wrote this primer, which was posted on the website for some of the background materials. And I wanted to just point out that this really matters, this difference of the interaction when you think about a material. X-rays, we all get X-rays, right? We break a bone, or we, God forbid, might have cancer. We get an X-ray to detect the density difference, right, and see what's going on. And that interacts with the electrons. The neutrons, on the other hand, interact with the nucleus. And if you remind yourself that a hydrogen atom, the nucleus is only 1/100,000th, right, of the volume of the size. Therefore, it's about 10 to the minus 12 scattering cross section, the square, roughly. So neutrons go through, they don't see much, right? Because the nucleus is really small. So you can get amazing penetration in neutron. You can image a fuel cell, for example, use neutron imaging. And we don't have time to get into those types of things, but that's the beauty. The other thing is because neutrons, and this is a quantum mechanical thing, have spin, they interact with the magnetic structure of a material where photons and X-rays don't. So hard matter scientists working, really need neutrons to look at magnetic structure to get the flash drives in your computer, right? All this work is understood, the magnetic structure of materials using neutrons. So neutrons have some unique properties. Now let's take a look at some of them. One of the strange things, because it's a quantum mechanical interaction with the nucleus, is that it's not so obvious, right, as to how they interact with a particular atom, right? So you pick your favorite atom out of the periodic structure. I notice some of you seem to have favorite organic molecules, right? So, and molecules you work with, but think of your favorite atom, and here's the atomic number Z. For X-ray, because it's electrons, well, the electrons go up with Z, right, linearly. So, heavy atoms scatter X-rays, light atoms don't scatter X-rays because they don't have electrons, right? So, or not many electrons. But for neutrons, it's all over the map. It's an inherent quantum mechanical effect, and so it's not trivial. But you can use this to your huge advantage, right? One of the things we'll see is that some of the interactions are negative. All that really means is whether it's repulsive or attractive as a neutron comes up to the nucleus. So don't get bent out of shape about negative scattering link densities. You're going to square everything anyway, so don't worry about it. But it's just literally a quantum mechanical effect where you say whether it's repulsive or attractive interactions. So hydrogen is negative and has a certain value. Titanium has another value, so that's reasonable. So you could actually use neutron scattering and go through titanium, which you can't do with X-rays, right? It would block it, high Z number, right? So interesting, different opportunities. And we're going to take advantage of that. So scattering length density is the amount of scattering an atom has, right? Given the fact that it comes with a certain density. So we talk about summing up over the atoms, but how many atoms are there per volume? So scattering length densities are what we worry about. And when we put, this is a classic experiment, we do this demo when we do the really fundamental neutron scattering to, more like the undergraduates and the high school kids, you put the glass beads in water and they disappear, right? Why? Because refractive index is the same, right? Well, scattering length density is refractive index. Or refractive index is scattering length density for light, okay? Fair enough? So when we talk about scattering length density, if you don't like that term, just say, let's talk about refractive index for neutrons. And it's easy, right? And we all know, right? We can make things disappear or appear depending upon air, water, have a contrast in refractive index. Same thing with neutrons. If we have scattering length densities that are the same, we have no contrast, they're invisible, right? Things disappear, just like the glass beads in water disappear when you put them in. Are we okay with that? Once you get that concept in your head, you're fine. Everything else is just math. And you say, well, okay, I've got to calculate the refractive index for neutrons, scattering length density. How do I do that? Well, I've got a chart full of data that's out there, and I can just sum up over all the atoms, and I'm done, right? So it's nothing more than that. It's just a sum over all the atoms in the system divided by the volume of the system, if you want. So we give this symbol rho, not to be confused with normal density, right? So sometimes we write SLD underneath, rho SLD, scattering length density, just to keep track of it. And it's going to be the distance, the difference between what my material is, my protein, and the water that it's in, for example. Okay, fair enough? And you can get these scattering densities online very nicely. You go to the NIST Center for Neutron Research. If you haven't noticed and you want to get online and download notes, hopefully nothing else, the NIST guest internet is really easy to, you just use it. So if you need to log into the internet while you're here, I don't know if we told people, but you just use the NIST guest. You just have to agree to be good about it and hit the agree and you're online. But you can then get to this website here, right? And use the scattering link density. You're going to use this. You're going to use it during the project. So it's easy. And we calculate something called coherent scattering, which we just talked about, and something called incoherent scattering, which is basically noise, incoherent, right? Coherent means there's some information content in there associated with the structure, and incoherent means it's the noise. And we're going to see where that comes from now. But let's talk about that contrast. I like this cartoon. It gives you a sense. If I have a protein and a polymer that have a different chemical composition, and they're in a solvent, which could be water, but we have deuterated water. Those of you who do NMR, right, you know about deuteration. Deuterated water, deuterium has a different scattering length than hydrogen, and it's easy to be substituted. And if you do that substitution in such a way that you match out the polymer, for example, the scattering density of the solvent can be adjusted to match the polymer, you only see the protein. And the opposite, if you match the protein, you only see the polymer. You can't do that with X-rays so easily, right? Light, you might do fluorescence labeling, right? But isotope substitution, really easy in the big scheme of things, right? And not changing the chemical nature of the material. Very powerful. So neutrons can sometimes do things that no other technique could possibly touch. Yes?
How do you obtain different isotopes? I mean, in terms of practicality, if you have...
Sure. Yes. So Fahid's question is, how do I get these deuterated compounds? There are deuteration facilities run by beamlines and governments around the world. There are chemistry groups who specialize in it. Often people in the NMR community, of course, use a lot of deuterated molecules, and you'll see some things coming from there. There are, Sigma Aldrich has a whole catalog full of deuterated compounds. So many of the simpler molecules and some polymers, right? There's various companies that specialize in it. And sometimes there are groups which will work with you around the world to do the deuteration of a particular lipid, cholesterol, things like that. It's doable, right? It's not easy. There are people who, how many people here grow bugs? I mean, do biology, right? Whether you grow things and make express proteins or anybody? Okay, but you know what I'm talking about. People can express proteins and molecules using biological synthesis methods, right? Bacteria, yeast, other things. What if you feed it deuterated sugar? You're going to get deuterated things coming out, right? So that's another way. Okay, good question. Fair enough? Yeah. Okay. And I realize I'm going fast because this is sort of just an introduction and an overview, whet your appetite, and then we'll get into the meat of the spin echo. We'll slow down a bit. Periodic table, neutron cross sections, again, all over the map. You know, you might look at things like gadolinium, boron on this chart, you know, oxygen. Some things have different scattering cross sections and others are high scattering, low scattering, scattering cross section. You know, how much distance can the neutrons go into the material before they're scattered, right? Think about that. Scattering cross section. Okay. A lot on this map, but if I take normal water, H2O, I could deuterate it, that's easy, and I get D2O, and I can mix it from pure hydrogen to pure deuterium. And the black line is the scattering link density, which starts negative for H2O and is largely positive for D2O. And that spans many biological systems of interest, lipids, saccharides, proteins, DNA, right? So you see, you can match out by adjusting this easily. So for biological and soft matter cases, often you're just deuterating the solvent. Cautionary tale, take a look at the protein here. You'd say, well, protein, I know its chemical formula, shouldn't it just have one value of scattering link density? It seems to vary with D2O. That's because there are some hydrogens on the molecule that are labile and will exchange, right? So if you put a protein in D2O, there's some, you know, free hydrogen, if you will, H plus, D plus, right? To exchange with the hydrogens that are exchangeable on your molecule, the amines and things, right? So just something to keep in mind. We use that sometimes, and you'll hear about that. Rose in the room. She's in the back, one of the students row here. You can talk to her. She does hydrogen deuterium exchange, right, to study fluctuations in molecules. All right. Neutrons have spin. And, you know, we try to describe this in some classical way. There isn't. It's a purely quantum mechanical. These are called fermions for the physicists in the room, because they spin 1/2. which says there are very, very distinct rules about what happens when a neutron interacts with another spin 1/2 object, right? Bosons are spin 1, right? Those are deuterium, and there are different rules for them. Anyways, neutrons have mass, they have spin, which allows them to interact with magnetic fields. That's why it makes them so useful for hard matter. And this is really important for neutron spin echo, because we're going to take this spin and we're going to manipulate it, as you're about to learn, right? That's the exciting thing. So in a magnetic field, the neutron acts like a top. I thought I had a top on here. And it spins and it precesses, right? So you're used to that. And you're going to see more of that in a minute. So there's a Lamar frequency, which is essentially like a spinning top, wobbles a little bit, and you'll see that. We're going to use that to study the materials. The nuclear spin then means, and this is important for the scattering, when we have coherent scattering, that's what we want often, but we also get incoherent scattering because they're isotopes, and if I look at any collection of atoms, right, some are going to be spin up, spin down, right, and they're randomly done. It's just statistical in a material. So you take a protein and you ask, what are the neutrons in the nucleus? What's their spin? Spin up, spin down, right? There's a certain population. And then there's interactions of my neutron with that nucleus. And so I get some that are interacting in a way that's called a triplet, for 2 spin ups for hydrogen interacting with a neutron, and 1 spin down, singlet state. And they have very different dense scattering lengths. And I need to average that over my sample, so I get some average value, and I need quantum mechanics to do this. The book that I'm passing around explains this very simply and nicely. So if you haven't had a lot of quantum and you don't remember all these rules for how quantum objects interact with each other, it's all in there, and we can go through the details, but that's not why we're here. We just need to know this happens. And so if we look at this, what we see is that the average, the square of the scattering length density, is a fairly large number for hydrogen because it's spin 1/2 and it interacts with the neutrons in a complex quantum mechanical way. It gives me the negative scattering density for the coherent scattering, and the fluctuations are large. And so if I take the difference between the root mean squared average, if you will, between the value that I calculate here and the square of that, this is the fluctuation. This is where I've lost information. So I'm getting scattering just because of the random nature of the spins in an object that I can't control and no one can control. And that gives me sort of a scattering that's not giving me any information other than there's something in the sample that has different spins up and down. It's not coherent. We call it incoherent. Now we can use that for some techniques, as you'll see. We can study that incoherent scattering. So it's not like it's not useful at all, but it's kind of a background scattering due to this fact that we're dealing with quantum mechanical objects, and they can be randomly spin up, spin down in a material. Deuterium is a boson, and it acts sort of fermion in a different way, and so this fluctuation is much less. So the noise in deuterated water is much lower. The background is much lower, okay? These are all quantum mechanics. At this point, you just need to know this, because you're going to see what happens when we go from H2O to D2O, what happens to our background, what happens to our coherent scattering. Why would if I want to look at dynamics, we'll see some quasi-elastic light scattering, why I might want to look at the hydrogen moving, because it has such a large incoherent cross-section, and that's what we measure in that technique. And in other techniques, we measure the coherent scattering. We don't want that noise. So we work in D2O not only to get contrast, but also to reduce the amount. So rather than deuterate a polymer and put it in H2O, we might deuterate the deuterium, use D2O, and use a hydrogenated polymer because we have a lot less hydrogen than in the system, because we have a lot more water in a dilute polymer system. Our background would be much lower. We get a much better signal to noise. So it's not equivalent sometimes, right? The amount of hydrogen you have in a system can raise your background, okay? Just something to keep in mind. Again, you're going to see this again. So, I'm just introducing the concept, giving you kind of a touchy-feely kind of idea that there's something there. And hopefully you've seen a little bit of this when you're reading before. So our scattering geometry, we have a probe and we have a sample now, which is some complicated things, and we have a detector. And so we have an incident wave vector Ki, we have a scattered wave vector Kf. Remember, these are just 2 pi divided by the wavelength, but they're actually vectors because they have directions, right? And we can look at the difference in momentum, which is related to this wave vector Ki by h bar, Planck's constant, right? And there's an energy and a momentum associated with each beam. And if you learn classical physics, you have energy and momentum, and you know these things are conserved. Same is true here. So we have to worry about this. They're going to interact with the sample. They might exchange energy, they might exchange momentum, okay? So we need to understand that, okay? So we have formulas for this, and what we measure at the detector is the number of scattered particles, or the field, if you will, of those particles, as an intensity, right? We measure it as the square, at a certain angle with a certain energy. So our detector, we may say, how many neutrons are coming to this detector with a certain energy, and I'm looking at a particular angle. So I need to set up the scattering experiment. And this is the scattering intensity, which is related to something called the differential scattering cross-section. It's the amount of scattering in this small area d omega, right? This little cross-sectional area. Again, the math, don't worry too much, right? The concepts are more important. So as we go along, we have to calculate that momentum difference, and momentum is just related to the values of the initial k and the final k, so it's related to the wavelength. And we have to calculate the energy difference, which is Planck's constant times the frequency of the radiation there. And so we can think about the scattering intensity as a function of both this q vector, which is the angle that I'm looking at relative to the main beam, and the change in energy due to interaction with the material, okay? And so we have a scattering function, and our static scattering is typically integrated over all this energy difference. So we're just looking at the angular dependence of the total intensity, right? And that's what we're going to be focusing on. And if the scattering is essentially, in many cases, elastic, that is, we're not really exchanging energy with the molecules in the system, then the energy going in is the same as the energy going out. The only change is a momentum change, and that's just a directional change, right? So kick the neutron and it goes off, scatters off in some direction, but with the same initial energy, the same wavelength. We talk about elastic scattering, no change in energy, and we get this IFQ, which is typically what we're looking at. I'm simplifying a lot here. We're going to get into this a little bit more as we look at the details of this. So I'm just going to go on. All right, here we go. So now we talk about this scattering intensity, and often we use this symbol for this elastic scattering, the scattering where we're not really exchanging a lot of energy with the sample, in terms of S of Q. And Q is a vector, and we start talking about it as a non-vector when we don't care about what angle it's, the rotational angle on the pattern. So if I have a 2D pattern, I just care about how far off am I, right? Circularly symmetric in many cases. But we'll see that. And so this scattering that I measure on at my detector, again, my little diagram here, is related to an integral over the sample volume of all the atoms and where they are relative to the angle that I'm looking at. So I've got to do this vector diagram for every pair of scattering points in the system and integrate over all possible interactions. That sounds bad, but it's actually not, right? When you get to simple geometries, maybe for a protein it's difficult. And then I might need a computer to do the calculation. But for simple objects, I can just say, oh, it's a sphere, equally probable of finding the atoms everywhere. I can integrate, as we'll see. Okay, so we have to calculate this scattering by summing up all of these possible interferences that end up on my detector here. From each of these apertures are just two randomly selected atoms in the system. And each one has their own strength of scattering, right? Carbon, oxygen, hydrogen. So I kind of need to know where they are, or if they're smeared out on average, that's fine, right? I can do the calculation. So what's the components of what we see? Each atom, right? How many atoms do we have? And how do scattering from two atoms interfere with each other? So now it kind of matters, right? Where the atoms are. Like if you put a bunch of atom of type 1 all on the outside of an object, that's different than if you uniformly distribute it throughout the object. Interesting, okay? So we can start to look at structure. So again, to summarize, because of the spin nature of the neutrons, we're going to get two parts of the scattering. We're going to get this part that I just talked about, this differential scattering cross-section, or S elastic, which depends on all the interference from all the atoms. That's the coherent scattering. That is information about where all the atoms are and what they are. That's this part. And we talk about cross-section, sigma, for that. related to the B, right, the scattering strength of each atom. And then there's the self part of the incoherent part, which is this background noise, right, because it's just due to this isotope fluctuation that we can't control and we don't know what it is. Hydrogen up and down, right, things like that, for spin. So my total scattering is the sum of what has information about the positions of the atoms and their type in the system and this background, okay? So let's look at a few static scattering functions. So we try to divide and conquer. I have a complex sample. I can calculate the scattering from an individual atom or a collection of individual atoms. So what I really need to do is start with an object, like a protein. Thank you, Ben. And just sum up over all the atoms inside this protein and maybe average over all orientations of the protein. And we call that a form factor. And that form factor is just a Fourier transform of this object. It's a three-dimensional Fourier transform. So in some sense, if you were mathematically oriented, you look at the equations that I have on the board here, and you say e to the minus I r dot q, where r is positions. That's a Fourier transform summed up over all the positions of the atoms and the atom type, right? M are all the atoms. And I square that. Why? Because it's field strength squared. We saw that. Intensity is the square. Okay? So, it's this, and which is nothing more than a Fourier transform. So it's the square of the Fourier transform of the structure. Sounds simple. The devil's in the details, right? How do we calculate that? Well, we have to do the sum. For some simple objects, that sum is easy because we can convert it to an integral, take a continuum limit and do the integral. Modern world, if you give me a protein structure out of the protein database, you know where every atom is, you know where they all are relative to each other, you can calculate this, right, on a computer by just doing the sum. And you have to do it for every scattering vector q or every angle you want to look at. And then you build up your I of q pattern for this object, for one protein. We'll talk about a collection of proteins next. Okay? So, again, I have scattering that's the background incoherent and the coherent scattering. The coherent scattering is the Fourier transform of the pair correlation function. We call that the pair correlation function, which is where all atoms are relative to each other in the system. And the incoherent is just this noise, if you will, this background noise, which is due to the fluctuations in the spins and the isotopes in the system. We could talk about a cross-section for coherent and a cross-section for incoherent. Again, this is always, important in each of these. And the coherent cross-section and the incoherent cross-section, you can look at some of the cross-sections up here for neutrons versus X-ray, and they're very, very different. You can do the same calculations for X-ray and light, by the way, right? Well, light, you talk about refractive index as a material property, but for X-rays, you would do the same type of calculation, a little more complicated, because the scattering from an atom is not just a number. It depends on the angle you look at. So if I now take my protein, right, and I think about a solution of proteins, I now have to sum up over all scattering, not just from one protein, but interference, for example, from a scattering center on this protein with that protein. That sounds horrible, but divide and conquer, right? So the first thing is we know how to calculate the scattering from one protein. That's not a problem. And all I need to do then is think about, well, okay, if I put the proteins, if I take a snapshot, an image of my solution, I know where the proteins are located, right? So this is nothing more than this convoluted. This is the convolution operator with this, right? So I get this by saying I put a protein and I decorate the positions with that protein and I get back this. Well, in scattering space, this is a multiplication. And so what you get is our overall intensity of the solution then is the prefactor A, which depends on the fact I have contrast between the protein and the water. If I match it out, this disappears and I don't see anything. I'm getting scattering, right? That's my prefactor. Then I've got a form factor, which is the square of that F of Q, the P of Q, which is the shape of the protein here, and we'll see some of these. And then I multiply that by a structure factor, which tells me that this point and this point and this point and this point, if I sum the scattering from just these points, I'll get this. There's a characteristic peak here because there's an average distance between the points, and that's roughly what that's telling me. So it looks bad, You'd say, oh my God, this is a nightmare to calculate. But dividing and conquering, when you look at the structure of this, you can just multiply through. So you first calculate your contrast, you calculate the form factor, and you calculate the structure factor. Or, given an I of Q, you fit it to these things where you know some or the other. And you'll see that in the workshop, each of the examples you go through. Okay? So, prefactor gives you information about the mass, the aggregate mass, the chemical structure of the material. The form factor tells you something about the size and the shape, or if it's an aggregate, the aggregate shape. And the structure factor tells you something about the interactions between these proteins, because if it's repulsive, they're going to want to stay away. If it's attractive, they're going to come together, and I'll see that in the structure. So if I say I want to learn something about protein-protein interactions or polymer-polymer interactions, I need to look at structure factor. If I want to know the structure of my polymer in solution, I look at form factor. If I want to know the composition or the mass of my object in solution, I need to know the prefactor. Okay? So the question, what to measure. So we'll look at some simple cases. If you have a dilute sample, then these are so far apart. This is just one, and this disappears. We can look at small concentrations of materials. We can look at concentrated materials. And you can sort of say, which of these terms is important as I do each of these. I'm not going to go through this in detail. You're going to go through this in the workshop as you design your experiments. So if I want to study a protein solution, I might do a series of experiments. Okay? How do I get these? SASView, online. Again, beautiful thing. You're going to learn a lot about it. You're going to use this software. I think many of you brought computers. Good. You'll be able to operate the SASView code during the workshop. Here's a nice pattern form factor for a sphere. This is then smeared because, turns out, neutrons aren't delivered all at the exact same wavelength. We'll learn about that. Okay? So there's a little bit of smearing, and so what you see in the experiment might look like the green curve, or the orange curve, or the red curve. There's some instrument effects, okay? And there's also a background term, right, that comes up. If I have a core shell particle, I could play the game of contrast matching. I could make it look like a sphere by matching the shell. I could make it look like a shell by matching the core, or I could have contrast difference between all three, and I get a complex series of curves. But by, for example, in this case, varying H2O D2O ratio, I could get three different curves that are all from the same object. Gives me exquisite information, right? It'll be okay. He's telling me I need to go. Gaussian coil, right? Gaussian coil, polymer, theory, model fit, experiment, data, learn something about the material. A couple of quick things. I'll just show you a few more. Slabs. There are a few limits that are important you're going to see in the workshop. One limit is called the Wagner limit. For very low Q, very small angles, right? What we see is we can expand out the theory, and what we find is we get something called the radius of gyration. This is model independent. So we don't know what the object is. We don't know what we're scattering from, but we could say it has a certain radius of gyration just from the I versus Q at low Q. You make what's called a Wagner plot, and you get information here. Again, I'm just summarizing these. They're all in there. You're going to work through these in some detail in the workshop. Another piece of information you can get is the Perot limit, which tells you something about the structure of the object. It's a polymer chain. You might have or a membrane. I have a fractal-like scattering. I get a power law scattering. I can also look at the surface of a material, the interface between the two materials, a particle, if I will. I get a fractal dimension of a surface. There's something called the Sands Toolbox, which is a very useful reference that's online, and I've given multiple places in this lecture where you can get to it. And it was written here at NIST, and it has many, many examples of this, what you get out. The SASView code generates these. You just say, I want something about that. So what do I get? If I have a cylinder, I have a Perot regime, although it fluctuates because of the structure, the interference pattern, on average it goes like 1 over Q to the 4th for a sharp interface. That's a Perot law here. The other part is up here for a cylinder, a long cylinder, 1 over Q, a rod-like object. This is a length of 400, a diameter of 20 angstroms, and so I get a regime. And then finally, I'll get a radius of gyration from the Wagner limit way down here. A lot of information I can get out just by looking at the pattern without doing a heavy-duty analysis. And here's another example of a fractal object with a mass fractal that should be proportional, but fractal dimension. here's light scattering, here's neutron scattering. Out here, we get the size of the primary particles is 36 nanometers, and we get a fractal dimension of around 2 here due to the cluster nature, fractal nature, so you get parode-like scattering, okay? So things you've heard about, maybe fractals and that. Polymers, Kratky plots, parode plot for polymers, very common. If you get a peak, it tells you a polymer with branching or structure in it, like addendum. Okay, so I'm going to skip this slide. I'm just going to talk about the fact, where do we get structure factors? Usually from computer simulations or theory that tell us where's the probability of finding another protein or another particle in solution or another polymer in solution at a certain distance r. And the Fourier transform of that is the structure factor. That's that SF2 part. So once I know the form factor for my object, and if I have a concentrated solution, then I have to worry about the structure factor. When it's dilute, basically nothing, the structure factor is 1, and I don't have to worry about it. So you might do a dilute scattering, work out the form factor. Once I know that, then I can measure the structure factor for a more concentrated sample. Okay? And I'll just show you that, for hard spheres, here's an example of that. The form factor for a sphere on a linear scale, and the structure factor times the form factor, structure factor here, multiplied what you would see in the experiment is the red curve. And you deconvolute that to the shape and size of the sphere and the interaction between the spheres giving me the red curve. Okay, so we're just about done. I just want to mention, where do you get the neutrons? Well, here we get them from nuclear fission. I think we're all somewhat familiar with this idea. I haven't seen the movie Oppenheimer yet, but I got to go see it because that's really an interesting, right? The development of the atom bomb. That's what happens when this gets out of control, right? So we have a little atom bomb here, a nuclear reactor that's in control, right? You have nuclear fission, right? And you generate the neutrons, but they have a lot of energy. You got to cool them down, so they go through the water, right? The moderators, and then they go through a chunk of ice. In this case, we want to put it through deuterated ice, but you put it through ice to cool it down. And so the wavelength of the neutrons gets longer and longer. They get slower and slower, and they get in a useful range for studying soft matter, polymers, things like that. So there are experiments right up against the nuclear reactor where they use the thermal neutrons, and then outside, after you moderate it and cool them down, the blue neutrons here, go through many, 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 many experiments, including the Neutron Spin Echo, which you're going to go see in a few minutes, well, later today, I think, on the tour. And the SANS instrument is used to measure that, where we bring the neutrons in, we pick the wavelength we want, we have a sample, and you will see one of these. And then there's a detector, which you can control the distance here, allows you to vary the angle a little bit. And this is huge. These things are monstrous. And you're going to get, if you haven't seen them yet, you'll get a chance to see these instruments. Here's a picture where we are, and back behind us, right, the guide hall up above and back behind us. Just an example of one instrument in a fisheye view. So I left an example for you to work through. We're not going to do it. We're going to now take a break. The example you could work through. It's just basic statistical thermodynamics, the Maxwell-Boltzmann. If I have neutrons, they have a wavelength. They come from a certain temperature. They'll have a wavelength distribution. All right? And that's important as we go along, that you recognize that unlike X-ray, where you get one wavelength, the neutrons, you have a distribution. You can use that to your advantage sometimes. And you could pick out what wavelengths or range of wavelengths you want to use. In this example, you can work through on your own just to make sure you understand a little bit about the neutrons. I just covered like a whole half a semester's worth of stuff in 40 minutes, right? So, but we wanted to get the terms out there. We wanted, you had a little homework to do before you came. So this should be somewhat of a refresher. If you didn't do your homework, there's late tonight, right? There's to go back and look at things. There's the book, which I would like back at some point, that's circulating around.